In heat transfer analysis, we should repeat same steps we performed in DC conduction analysis. In QuickField, I create new problem. The problem name would be heat transfer limiter. Next, the problem type is steady state heat transfer and the model class is three-dimensional import. Okay, here we should import the step file and assign labels to bodies. First click to select the face, second click to select the body. Porcelain. Hide. Again, first click to select the face, second click to select the body, and to select multiple objects, hold the Ctrl button pressed. These are covers. Now these are conducting parts. First click, second click. These are terminals. These are stickers. And this is the fuse. Unhide all bodies and assign boundary condition. The outer surface is cooled by the air. So I select the outer surface elements. Remember to hold the Ctrl button pressed to Now that's enough. I do not select terminals because the terminals are connected to some other parts. So these faces I give the label external. Now let's assign physical properties. For the external faces I specify natural boundary condition with the ambient air temperature of 20 degrees Celsius and the convection coefficient of 10 watts per Kelvin meter squared. Okay. For the porcelain body I specify thermal conductivity of 2. For the steel covers, I specify thermal conductivity of 40. Now for each copper part, we specify thermal conductivity of 380 and heat power source density. Please pay attention to the units, which is watts divided by the meter cubed. So for the fuse I type in power divided by the volume. Okay. And the same for the stickers. Thermal conductivity 380. The par is this value divided by the volume. Okay, and for the terminals, thermal conductivity 380, par is here, and this is the volume. Now let's review the model. We have the porcelain body, we have steel covers, and we have conducting elements. But the sound is missing. Inside the porcelain body we should have the sound filling, but it is missing in the model. There, inside should be the sound filling. We will add the surrounding box, the background region. This background region surrounds everything and penetrates inside. For this box I will assign the label sound, and the thermal conductivity of the sound is 0.25. Okay. It's a bit tricky here. We have the sound inside, and that is okay, but the sound outside. In fact, the outer sound will not ruin the model. We have specified boundary condition. So the heat flux coming from inside, from the fuse, will be eventually removed from these faces. And we are interested in the temperature distribution only inside. What is placed outside these boundary conditions is no matter for us. So we have only fuse, sound filling, porcelain case, and boundary condition. Okay, now let's build the finite element mesh. I will again just click the button and start the simulation. Save all simulation files. Simulation result is ready. And here we can see the temperature distribution. Now let's take a look what is inside. I will use the cut plane, change the picture settings and hide the plane. So the fuse temperature at the rated current is about 44 degrees Celsius. Again, how to verify our model? First, let's make sure that outer sound doesn't affect the model. I will change the presentation type and switch to the heat flux, and will adjust the heat flux picture. you can see there is a heat flux inside, and once the heat flux reach the boundary condition, the flux is removed. There is no heat flux in the outer sand. The path of the flux is the following: fuse, sand filling, porcelain body, boundary condition. So our assumption about the sandbox and the boundary condition was correct. Now let's verify powers. I will calculate the total power for the fuse. So I switch to the integrals and click the label fuse in the tree. Here is the total power, which is 1.82 watts, but it should be 1.93. Let's calculate the discrepancy. I'll start the calculator. 1.93 minus 1.82 divided by 1.93. So the discrepancy is 5%. Can we reduce this value and get more accurate solution? Well, accuracy depends on the mesh, on the finite element mesh density. So to get more accurate solution, I should open the geometry model and adjust the mesh density. That's easy. I select all objects and switch to the manual value of the spacing. And I will switch on the spheres to indicate the spacing values. Now you see that at this vertex the spacing value is 0.315, and if I change the spacing value, I will get higher mesh density. I can adjust the spacing value for entire group of elements, 0.01. And I can adjust the spacing for the fuse. Right click, hide all but this. Oh, you see. Now I will select this with the rubber band and type in some smaller spacing value, or even smaller value. Okay, unhide all. Now we can build the finite element mesh for edges, for faces, and for the volumes. And run the analysis again. The simulation is finished. Let's take a look at the result, and let's again calculate the integral heat flux for the fuse. And the heat flux now is 1.85. It was 1.82, now it is 1.85. Calculate the discrepancy. 1.93 minus 1.85 divided by 1.93. It was 5.6%, now it is 4%. If you need better accuracy, just build more dense mesh. Now that's all. We have simulated DC conduction problem and calculated current density distribution and found the Joule losses in the elements. Next we have simulated heat transfer problem and used these losses to find the temperature distribution.